Okay, thank you, Francine. So let me remind you of where we were at the end last time. Given an indexed family of smooth functions, so alpha is the M, it's infinity on Rm. I'm saying Rm, but it could also be just on or on an open set omega. Okay, so but then there exists this infinity function fxy on Rm cross Rm or omega cross some open set such that the y derivatives are prescribed over, say, beta factorial equals f alpha of x for all alpha. Notice that, you know, instead of taking f sub alpha, if I take, since these are arbitrary, if I take them to be, this doesn't make sense, does it? F beta. If instead of taking them to be f alpha, if I take them to be alpha factorial times f sub alpha, then it means these derivatives will be exactly f sub alpha, right? So, all right, and I left this as an exercise, and I told you that you just followed the way the Borel's lemma was proved. Okay. Now here is one application of this. So lemma, the numbering is lemma 5. So let's f be a infinity function on Rm. Again, as I said, or you can take any infinity function on an open set. Then there exists a function f of xy on Rm cross Rm that is an almost analytic extension of little f, meaning so such that capital F when y equals 0 is f of x, and 2 when I take d bar of f of xy. Okay, so if I take df by dz j bar, then this vanishes to infinite order. They're flat. So this equals this for all n. Okay? Okay? So note that I remarked this already, but let me repeat it, saying that, you see, in this case, capital F is supposed to be smooth. So saying that a smooth function satisfies this is the same as saying, so the 2 is equivalent to saying that if you take all order derivatives in y of this function and evaluate at y equal to 0, that this should be 0 for all beta. Okay? That's the same. Okay? Okay. So, so how are we supposed to prove it? Well, look, what I'm going to do is, of course, as I said, these things are not unique. Okay? For example, okay, so so we are going to try and see the conditions that are being imposed on capital F. Well, so we want, clearly, we want f of x0 to be f of x, okay? And now we want for df by dz bar at y equal to 0 to be 0. Now, what is this? This is, you know, 1/2 df by dyj by dxj plus I square root of -1. So you want this to be 0. So want 0 to be equal to this, which means that you want df by dyj at x0 to be what? You want it to be I times df by dxj at x0. But this is already determined because you see, you know f in x space, and so you can calculate this. So this is the same as this then at x. Okay, so the first y derivatives of f are determined. Okay, so f is determined when y is 0, and the first y derivative is determined when y is 0. Next, I try to determine the second order derivatives in y of f. Well, so by induction, so suppose, and they are determined in terms of f and its derivatives. Okay, so suppose for some multi-index beta, suppose these are already known. Suppose this equals this is determined or expressed in terms of f of x and its derivatives. Let me now see how I can determine the next order derivative. You know, if I differentiate in y, if I take dy with respect to beta plus ej. Okay? So what I do is, well, I look at the following. So remember, you want all order derivatives in y to be 0. Okay? All order derivatives to be 0 at y equal to 0. So want 0 to be, in particular, dy by d beta of df by dzj bar, which means xj at x0 plus I df dyj at x0. You want this to be 0. This is the same as saying d by dxj of dy beta of f at x0 plus this, and this gives me dy beta plus ej, right? One more, I f at x0. Which means that, see, 0 equals this, so this means that dy beta plus ej of f at y equal to 0 has to be I times d by dxj of dy beta f of x0. Notice that by the induction assumption, you assumed that this is already expressed in terms of a little f of x and its derivatives. So this is expressed in terms of f of x and its derivatives. Therefore, this is known because you are differentiating in x. So this whole thing is expressed in terms of little f and its derivatives, and hence this can be expressed in terms of f and its derivatives. Okay? Okay, so thus there exist functions f beta expressed in terms of f and its derivatives such that the y beta or y alpha, f at x0, has to be those functions. Okay? Oh, but we know from the exercise that such a function exists. Okay? We know such a function exists. Okay? So by the exercise, such f exists. And then you just have to check that such an f does indeed satisfy this. Okay, so I leave it there. Okay. Okay, so a smooth function has an almost analytic extension. Okay, so f is called an almost analytic extension of little f. Almost analytic. You'll see how we will use this. Okay, to study regularities of solutions of vector fields, an almost analytic extension of little f. All right, well, now next comes a theorem. Okay, so theorem 6, let little f be continuous on Rm or on an open set omega, then little f is C infinity if and only if there exists just a C1 is enough. C1 function capital F of xy such that at y equal to 0, f is little f of x, and f is an almost analytic extension. Okay, so d bar f. So capital F is C1, so I can differentiate it once, and this is O of y to the n for all n. Okay, this is nice because a smooth function is expressed in terms of a function capital F, which is C1, just C1. Okay. All right. As I said, you'll see how this kind of thing will provide appropriate replacement for the formation of contour when you are dealing with integrating holomorphic forms. Okay. Okay. And the proof will not be bad. One direction, we actually just proved it. We already know that that if little f is C infinity, in fact, we showed there is a C infinity capital F satisfying this. Okay, so that direction is already done. So proof, this is done with, in fact, with capital F C infinity. And so let's do this direction then. So you have f, capital F is C1, f of x0 is little f of x, and d bar f is flat at y equal to 0, meaning this is this for all n. Y is little f smooth. Okay? Well, one thing we know about one way we know to prove a function is smooth is using Pelley-Wiener theorem. So I look at the Fourier transform of f. Well, f may not have a Fourier transform. It may not, the growth is not controlled. But when you study smoothness, you only have to study it near a point. So I localize. Okay, so I take a point. So let x naught be in Rm, phi of x, a C infinity function of compact support, say in a ball. Okay, this is some ball containing x naught, and phi equal to 1 near x naught. Okay, so if I prove that phi times little f, its Fourier transform decays rapidly, I'm done. Phi times f is C infinity, therefore f is C infinity at x naught, and x naught is arbitrary. All right, so the Fourier transform, okay, so E minus ix dot c, phi of x, f of x, dx. All right. Now, this little f is smooth, therefore it has an almost analytic extension. So let capital phi of xy be C infinity, such that capital phi x0 is phi of x, and d bar phi flat at y equal to 0. Now, if you remember the construction was that this capital F, you see, in the x variable, if these functions are supported in a given ball, then in the x variable, capital F is also supported in the x variable from the construction. Okay? And so therefore, in the x variable, this phi of xy will be supported in this ball. Okay? So note that the function x going to phi of x for any fixed y is supported. So just go back and look at the construction. Is supported in the ball B for all y. I'm going to deform contour. Now you'll see what I meant by, a replacement for deformation of contour. To estimate this, I'm going to deform contour, okay? So basically, I'm going to replace phi of x by capital phi of xy. I want to replace little f of x by capital F of xy. And as I said, I mentioned before, the thing is deformation of contour is nothing but Stokes theorem. Okay, so let's see how that is so. Okay, so so this is what I do. First, let C naught be in Rn. Okay, take any point in Rm rather. C naught different from 0, and in fact, say norm of C naught equal to 1. This kind of thing is going to appear again and again. So let me do it once. Okay. So now let's okay. So let y naught be a fixed point in Rm such that C naught dot inner product y naught is negative, is some number negative minus c. Okay, you see? Now, so you see, so here is c naught. Okay, so y naught is somewhere here. Okay, the thing is, if this is negative, then c naught is a unit vector. Then in fact, I can take a conic neighborhood of c naught, such that for any c here, c dot y naught will remain negative. Why is that so? You see, this is a conic condition. If you multiply c naught by lambda, it will still be lambda positive, it will still be true. Well, here is the thing. There is delta positive, such that if eta is in Rm, which is within delta of C naught, then eta dot y naught will be less than, at least will be less than minus c over 2 by continuity. Okay, by continuity. Okay, I'm just changing C naught a little bit. Okay, so this is in the unit sphere. Here is C naught. So there is some neighborhood here. This is where the etas come, where this is satisfied. And now let me define this cone generated by this small neighborhood of the unit sphere. So what is that cone? Let gamma be the set C in Rm such that, I take any C such that when I bring it to the unit sphere, such that C over norm of C, when I bring it to the unit sphere project, then I am inside this neighborhood. What does that mean? That this minus C naught is less than delta. Okay? This is an open cone. A cone means a set where, given a point in the set, a positive number lambda times that point is also in the set. Okay? So this is a cone. Gamma is an open cone. Okay, now I will take a point in gamma now, a vector in gamma, and see what the inner product with y naught is. Okay. Now, if C is any vector in gamma, you see in gamma, because C over norm of C satisfies this, I have this. And so C dot y naught is going to equal C dot C over norm of C dot y naught times norm of C. But this is less than minus C over 2. Okay? So this is less than minus C over 2 norm of C. Okay? Okay, now let D be the following domain. D is the ball in X space cross, well, let me put it this way. Let D be the set of all x plus ty, where x comes from the ball, t y naught rather, and t is between 0 and 1. Okay. Okay, so what is this d? It's a cylinder. Okay, so the base when t equal to 0 is b, and this over here is b plus y naught. Okay, b plus y naught, and so these are points inside here. So you have this set, and if I take a function g, so note that. So this is, I'm going to show you how I use the Stokes theorem. If I take a function g of xy, and well, not a function, but a form, this form, okay? So, so here the zj mean x plus iyj, okay? J are xj plus iyj. So if I take a form like this, okay, and if I integrate the differential of this form over this set D, you see this is an m plus 1 form, and this set is m plus 1 dimensional. You know, the x is in B, the m dimension, and then this is 1 dimensional, right? So on an m plus 1 dimensional set, you can integrate an m plus 1 form. Now, this equals, by Stokes theorem, so maybe let me know, the integral over the boundary of the different over the boundary of rather g dz1 dzm. Okay, but now this thing, this integral equals, when you take the differential, because this is already the wedge product of d of things, it's dg wedge dz1 wedge dzm. Now the differential of a function is the sum of dg by dzj bar plus dg by dzj, right? So this wedge dz1 dzm. From now on, I'll abbreviate this as just dz. Okay, dz will mean dz1, the m form. Okay. All right. Now notice this wedge. This is 0, and therefore what you have is something that only involves the Cauchy-Riemann operators over d of dg dzj bar dzj bar dz. Okay, so I'm going to apply this to the following, to basically the almost analytic extension of this. Little phi has this as almost analytic extension, f has capital F of xy, and this guy is holomorphic. It has holomorphic extension, right? I replace x by z, so then I get the following. So remember, the goal is to prove that this Fourier transform decays rapidly in this gamma, at least. Okay. So, so we have the integral e minus I z dot c capital phi xy capital F of xy. So dz, remember, means dz1 wedge up to dzm. Okay. So the integral of this over the boundary equals, as we saw, the sum j double integral d by dzj bar of the integrand e minus z dot c phi xy. Z means x plus iy here. Okay, so capital F dzj bar wedge dz over d. All right, now the thing is, you see, phi is supported in here, remember, support of capital phi as a function of x is in B, remember. in B. So when you integrate over the boundary of D, there is a lateral surface, there is the top and the bottom, right? On the lateral surface, it is 0 because phi is 0 on the boundary of B. So what remains is really y equal to 0 and y equal to y naught. Okay, so this integral is the integral. Okay, when y equals 0, what do I get? Z becomes x. When y equal to 0, this is phi of x, and this is f of x. In other words, it's exactly the things that I'm trying to estimate. Okay? Okay, that is when y equals 0. And at y naught, it is integral over b. So let me write it as equal. I'm going to write it to the other side, okay? So it will be e minus I x plus I y naught dot c. And this will be phi of x y naught, f of x y naught. Y is fixed, so this is really dx. Okay, dx1, dx2, up to dxm. Okay, so that is the boundary integral. The solid integral, so I have to take d bar. When you take d bar, this is holomorphic, that is 0. So there are only two terms that come up. And because each of them are almost analytic, okay, the product is almost analytic, and therefore what I get is a sum of things of the following form. E minus I. Now z dot c, let me write z as x plus I ty naught now, because that's what a generic point is. And then I get the almost analyticity gives me, so y is now ty naught, so I get O of ty naught to the power of n. Well, y naught is an n0 vector, so this is really the same as to the n. Okay, that's what I get. Okay, dz j bar dz. All right. So in order to show that this decays rapidly, you see that this is less than or equal to a constant c sub k over norm of c to the k for any k, I have to show that this decays rapidly and this decays rapidly. Well, this actually decays exponentially, even better, okay? Reason, because y naught dot c, where is that thing? I don't remember, but y naught dot c, so recall that for c in gamma, what did we have? Didn't we say y naught dot c was less than minus c over 2, right? Is this what we said? Huh?
Why there is an equality sign here?
Huh?
There should be a summation sign.
What?
This equality.
Yeah? Well, this integral has two pieces, the top and the bottom. Here is the top. The bottom, I take it to this side. Oh, this plus there is this also. There is this also, sorry. That's what I mean. Sorry, yeah, you're right. Yeah. Okay? So you see, so y naught dot c is that minus c over 2 norm of c. Therefore, this is decays exponentially. Okay? So therefore, this part, x plus I y naught dot c, phi of x y naught, f of x y naught. Okay, this is negligible. Less than or equal to some constant coming from the sup norms of this, or their integrals, e to the minus c over 2 norm of c. Great. So this is what we have to deal with. So let me take one of the terms. Okay, let me estimate that. If I estimate one of these integrals, oh, there is dot c. T y naught dot c. There is I here. O of t to the n. Okay. This is what I have to estimate, basically. Don't worry about the form. So here I get the norm of this will be e to the power of t times y naught dot c. Well, y naught dot c is less than or equal to minus c over 2. And so I get the integral e minus c over 2 t times norm of c. So the thing is, you see, this t can go up to 0, okay? T is between 0 and 1. So when t becomes 0, this doesn't help me at all, okay? But look, but I have this, okay, of t to the n, okay? So for any n, so I have Cn, so t to the n dt. Well, then I use an elementary inequality, namely, you know, if a is positive, e to the a is bigger than or equal to a to the n over n factorial, right? And therefore, the reciprocal, which is what this is dominated by, well, take the 1 over, okay, so some constant, 1 over t to the n times c to the n. Okay? This can be bad. T can go to 0, but it's killed by this. That's where I'm using almost analyticity. Okay? Okay? And therefore, I get exactly the polynomial decay. Is that clear? Okay? This sort of thing is going to appear and reappear in different forms. Okay? So therefore, what have I shown? I've shown that the Fourier transform decay. So I took a point C naught. Where is it? Didn't I say let C naught be in Rm somewhere? Norm of C naught equal to 1. Anyways, I took a, so this is what we have shown. So shown the following. Given a C naught in Rm, you know, on the unit sphere, there exists a cone gamma containing C naught such that phi u, not phi u, phi f hat of C decays rapidly. You see, okay, for all n, for C in gamma. But I'm supposed to show this for all C, not just in one column. But that's easy. You see the unit sphere is compact. So each C naught, for each C naught, you already showed there is a neighborhood where this happens. So then use the finite cover argument. Okay. So use combine and the proof finishes. Okay. Again, this is you see because the things you are trying to do are conic in C. All you have to work is really on the sphere. Okay. So since the sphere is compact, we are done. Okay? Any question? Okay, now next I'm going to give you a quick introduction to something called microlocal analysis, okay? Which is a refined way of studying singularities of functions. So, and this, part of the reason why I wanted to introduce you to almost analytic extensions and so on is because there are many notions in microlocal analysis that become easier to understand, more intuitive when you use almost analytic extensions. Okay, so this is not how most people do it, but you know, people with some inclination towards complex analysis probably prefer this. Anyways, let me first give you the definition. What is a wavefront set? Okay. So definition. So when a function f is not smooth, it's because the Fourier transform. So say f is. So suppose you want to study smoothness at x naught. You localize f. So you may assume f is of compact support. Okay. Or just take phi times f. Phi 1 near x naught of compact support. So when f is not smooth at x naught, it means this is not infinity. And by Pelly-Wiener, it means that there are directions where this is not decaying rapidly. It's still possible that there might be some directions in which it decays rapidly. And so we isolate those directions in which it decays rapidly. Those are the good directions, okay? So the definition is the following. So let U be continuous. Again, it can be any open set, but I'm going to say Rm. It can also be a distribution, but I will work with continuous functions, okay? And take a point x naught in Rm. If I take a direction, difference from 0, we say the point x naught dot c naught, comma c naught is not in the wavefront set of U. Okay, so WF stands for C infinity wavefront set, because I'm going to talk about analytic wavefront set also. Wavefront set, okay, of U. That's how this is to be read. If there is phi, smooth function of compact support, phi of x naught phi equal to 1 near x naught, or actually it's enough to have phi of x naught non-zero, okay, just phi of x naught non-zero, and a conic neighborhood of c naught, and gamma containing c naught, a cone. So you know what a conic neighborhood of c naught is, huh? Such that, what is it? It's U, not F. Huh? U. Such that this decays rapidly. Okay? Now, so this point will then be, so in that case we say U is microlocally C infinity at x naught c naught. Now let me explain a little bit the term microlocal. You already localized because you are trying to study smoothness near x naught, so you localized. That's where the local comes from. After you localize, to study the singularities of phi U, to study where it is not smooth, Pelley-Wiener tells you have to look at the Fourier transform. And so now, so we look at the directions in the Fourier transform where the Fourier transform does not decay or does decay rapidly. Where it decays rapidly, those are the good directions. Huh? But it's an unfortunate part of the definition, an unfortunate convention that unfortunately we are using a negation to define the good direction. Okay? But remember, to say something is not in the wavefront set is good. The things that are in the wavefront set are those directions for which there is no conic neighborhood such that there is a rapid decay. Okay? I'm going to relate this to partial differential equations in a moment. Okay? To partial differential equations, at least the basic ones like the Laplace operator, the wave operator, and so on. Okay? But okay. So now let me say another thing. Smoothness, as you know, is something that you can study on a manifold, right? You can talk about a function being smooth. It turns out that microlocal smoothness you can also define on a manifold. That is the nice thing about it, because these things turn out to be cotangent vectors. If you use a diffeomorphism and you look at your function, your new function under the diffeomorphism, it turns out that the wavefront set of a function changes the way cotangent vectors change. You know, the transpose of the differential of the function, you know, that kind of thing. And so therefore, you see, these are invariantly defined. That's very nice. Okay? These things, wavefront set is invariantly defined. Okay? Hormander was the one that systematized it, but the Japanese also had an approach to this. The Japanese used something more in the spirit of almost analytic extensions. So I'm going to relate this. Okay, so this may not be intuitive for you now, and don't blame yourself. This is not intuitive at all, this definition. Okay, unless you have worked in with zero differential operators and so on, it's not intuitive at all. But today I'm going to try and make it intuitive for you by expressing this using almost analytic extensions. Okay, I'll do that in a moment. But first, let me next define what is meant by the real analytic wavefront set. So let's call this, I guess, definition 1, definition 2. So same setup, U continuous on a Rm, x naught in Rm. Oh, one thing I should immediately say here, it's easy to see that, so fact, very easy to fact. So how is this related to the smoothness of U? Well, U is infinity near x naught. If and only if the wavefront set of U at x naught, in other words, if and only if, so the wavefront set of U at x naught is 0. That is, if and only if x naught C is not in the wavefront set of U for all directions. We look at only non-zero direction, okay? That's how it's related. Now, the way to see it is, well, if you use infinity near x naught, Pelley-Wiener tells you this is true in all directions. So this will be satisfied. Conversely, if this is not in the wavefront set, then for all directions, in particular, it's true for all directions on the unit sphere. The definition, you see, this is a conic thing. If it holds for C, it holds for lambda times C, because you are in a cone. So if this is not in the wavefront set, for all C, it means it's not in the wavefront set for all C on the sphere. Okay? So you get a cone around each point, use compactness, blah, blah, and then you get the Fourier transform decays in all directions. And that therefore by Pelley-Wiener, U has to be smooth, okay? Okay, so this characterizes the smoothness, the notion of wavefront set, but it goes beyond that. It refines the smoothness, okay? It refines the smoothness. It also, isolates the directions where smoothness may fail, or isolates the directions where smoothness in terms of Fourier transform is okay. Okay, now the analogous thing for real analytic functions. Take x naught in Rm. If C naught is non-zero, we say x naught comma C naught. Again, this turns out to be a cotangent vector, is not in the analytic wavefront set of U. So I use the A as a subscript here. So this is the real analytic. This is the real analytic wavefront set of U. If, well, what is it that replaced the Fourier transform for us to characterize analyticity? Remember? The FBI transform, okay? If there exists phi as here, C0 infinity, phi of x naught is 1, less than 0, and cone gamma containing C cone, such that the FBI, and in the FBI there are two variables, and the neighborhood. No, I don't need. Neighborhood V of x naught, such that the FBI of the function phi times U. Okay, the FBI decays. Well, this time it has to be this for all C in gamma. Okay, this is what characterized analyticity. Okay, but now we are saying analytic in certain directions, and as before, we have a corresponding fact. Namely, a function U is real analytic at x naught or near x naught if and only if x naught C is not in the analytic wavefront set of U for all C. Okay, it's not obvious yet, but you see, one thing you expect is the following. Real analytic functions are infinity in particular, right? So you expect that if microlocally something is real analytic, okay, you expect it to be smooth, okay? It's not obvious now, but I'm going to show it, okay? It also is not obvious that this is invariant under an analytic diffeomorphism, just as it was not obvious that this is invariant under a infinity diffeomorphism. That also will come as a simple consequence of my characterization of these concepts using analytic or almost analytic extensions. Okay, and so let's come to the following theorem now. I'm trying to check the numbering. Theorem 7. Now, this is what will make. This is what I promised you before. This is what will make this notion, infinity wavefront set, more intuitive, much more intuitive. Okay, and there will be an analogous, more intuitive way of describing this. Okay, so let U again be continuous. Everything I said is fine with distributions. Okay, let U be continuous on Rm. You take a point in R. Okay, let's take a direction C naught in Rm. Then X naught C naught is not in the C infinity wavefront set of U, which basically, remember, means the Fourier transform behaves appropriately, nicely, decays in a conic direction of C naught. Okay, so this is a good direction for you if and only if there exists a finite number of cones, gamma 1, gamma n, finite number of cones, a neighborhood V of X naught. These cones have the property that C naught dot gamma j is negative, okay, for all j. If you take any vector in here, dot production, and almost analytic functions. Let me call them uj, u1 xy, up to un xy, uj defined on v cross gamma j, okay, such that your function u of x is the sum of the values of this uj at y equal to 0. Now, isn't that nice? This is really a much simpler way of understanding what infinity wavefront set is. Let me make it more concrete by looking at the simplest situation when m is 1, in dimension 1, for example. Let's see what in dimension 1 what this means. Okay. There will be an analogous thing for analytic wavefront set. You have to have cones like this, whose dot product with C naught less than, but then you want holomorphic extensions, not almost an holomorphic. Okay, that will characterize analytic wavefront set. Okay. So let us look at this case m equal to 1. So you take a continuous function in the real line. When you study the Fourier transform in terms of wavefront sets, there are really two directions. You see, the unit sphere in the real line is what? 1 and minus 1. You know, this thing is. So if 1 and minus 1 are not in the wavefront set, the function is smooth. But in general, maybe both 1 and minus 1 are in the wavefront set for most functions, or maybe 1 is not in the wavefront set, or minus 1 is not in the wavefront set. Okay? So you only have to check 1 and minus 1. Okay? So check at any point x naught, check this and this. That's the only thing. So saying that x naught minus 1 is not in the C infinity wavefront set of U, according to this theorem, means is the same as saying this is equivalent to saying there exists almost analytic function u of xy for y positive such that u of x0, or I should call it u tilde, such that this equals u of x. In other words, near x naught, near x naught. So near x naught, okay, there is a function u tilde defined here that's almost analytic. Okay, so it's not defined in a neighborhood of x naught. If there is an almost analytic extension of u of x in a neighborhood of x naught, remember we proved that is the same as saying u is smooth. Okay, Well, this is partial regularity. U is not quite smooth, but there is almost nothing on one side. In saying -1, this one is not in the wavefront set, means there is U tilde from the bottom side. Okay? Is that clear? This should make. Now, in higher dimensions, what this is saying is a similar thing. This, the sets where these UJ are almost analytic are sets like this. These are called wedges. It's just that, that in one dimension, in the plane, in one dimension, wedges are easy to describe. It's either this or this. This is the product. Whereas in higher dimensions, so wedge, so you have the open set V, and then you have directions, you know, these cones based at each point. Okay? Now, let me tell you, perhaps the most basic fundamental result in microlocal analysis, what justifies the introduction of this, the idea of wavefront set, okay? Or what can be termed as the gateway to microlocal analysis, okay, is the notion of ellipticity. So you take a differential operator, P, of any order, okay? A alpha of x, d alpha, alpha less than or equal to some number L. Then to this differential operator, you associate what is called the principal symbol. So you replace D by C. Maybe you have seen this in your PDE course. This is called the principal, the main symbol. Okay? The principal symbol usually contains a lot of information about the operator itself. For example, regularity of solutions and so on. Usually, not always. Okay? Like the hit operator, for example, is hypoelliptic and his solution is smooth, but that's not captured by the principal symbol. Anyways, so then there is what is called the characteristic set of P. It is the set of points xc, c different from 0, such that the principal symbol is 0 there. Okay? That's called the characteristic. This is the bad set. This is the bad set. When you study the equation Pu equal to F, problems happen basically because this set is a bad set. Now, the best kind of operators are then operators where this is empty. So we say P is elliptic if the characteristic set is empty. Okay? So a good example, a very good example, the standard basic example is the Laplace operator. If you look at the symbol, what you get is norm of c squared, and this is 0 only if c is 0. So the characteristic set is empty. Okay? Now let me tell you the fundamental theorem I said, which can be regarded as a gateway to microlocal analysis, is the following. If you have P, if U is a solution of an equation, then the bad directions, okay, so you want to study regularity of U, the bad directions are contained in the union of the characteristic set of P and the wavefront set of F. You see, if F already is bad, you can't expect to get anything, you know, for U. But you see, this implies the following. If F is infinity, then the bad directions are contained in the characteristic set of P. So if the characteristic set of P happens to be the empty set, meaning if P happens to be elliptic, then the wavefront set is empty, meaning U is smooth. Okay? Smooth. You get the elliptic regularity. Is that clear? 2. But this tells you things even for things that are not elliptic. If you take the wave operator, so let's take the wave operator. Okay? Then I'll finish in 2 minutes. Okay? Then you see for the wave operator, the principal symbol, let me use tau squared minus norm of c squared. So the characteristic set is where this is 0, meaning norm of c equal to tau. This is usually referred to as being the light cone. Okay? According to this, then, you know, the wave operator is not smooth, right? There are solutions that are not smooth. But although it's not smooth, the Fourier transform will decay rapidly everywhere except on this cone. Okay? So you get that information. Is that clear? Now, this is if P has C infinity coefficient. If it has real analytic coefficients, The same is true with real analytic wavefront set replaced by simplity wavefront set. I will stop here. I'll take questions.